Section 4.3, using derivatives to graph functions. So the first 2 pages of these notes is a table that we're going to fill in with some information that we know about first derivatives and second derivatives and what they tell us about graphs. So, first derivative is the first derivative test. And when we find the second derivative, that would be our second derivative test. And each test tells us something different about the original function. So the first derivative test, if our y value for the derivative is positive, so if f prime of x is greater than 0, then that tells us that f of x is increasing. Right? If f prime of x is less than 0, then that tells us that f of x is decreasing. Right? So that basically says that our graph of f of x is going up, our graph of f of x is going down. Okay? For our second derivative test, if f double prime of x is greater than 0, then that means f of x is concave up, which means it can look like this, or this is a curve, by the way, or it can look like this. Okay, the point is that the curve in our graph is facing upwards. If f double prime of x is less than 0, then f of x is concave down. So that can look like that, or it can look like that. In this case, our curves are opened downwards. So if we have a positive first derivative test and a positive second derivative test, then, so if f prime of x is greater than 0 and f double prime of x is greater than 0, then we have a situation where we have an increasing concave up, which looks like this. Okay, if f prime of x is greater than 0 and f double prime of x is less than 0, then we have an increasing concave down, which looks like this. If f prime of x is less than 0 and f double prime of x is greater than 0, then we have a decreasing concave up, which looks like that. And if f prime of x is less than 0 and f double prime of x is less than 0, then we have a decreasing concave down, which looks like this. Okay. Alright, let's look at the second table and what that tells us. So again, first and second derivative tests. right? So if we think about this as position, velocity, and acceleration, f of x would be our position, f prime of x is our first derivative, which is also our velocity, and f double prime of x is our second derivative, which is also our acceleration. Okay, so if the function is equal to 0, so if f of x is equal to 0, that gives us x-intercepts. Right, it tells us the position of the function. Okay, if f prime of x is equal to 0, then that gives us critical points. Right, it tells us if we have a min or a max. Okay, if f double prime of x is equal to 0, that gives us inflection points. Okay, and that will tell us when we switch from concave up and concave down. So that tells us concavity. Okay. Right. So slopes. Right, the slope of f of x is equal to the derivative of f of x. Right? So if the slope is increasing, then the derivative is positive. If our slope is decreasing, then our derivative is negative. Okay? The slope of f prime of x is equal to our second derivative. So if the slope of f prime of x is increasing, then f double prime is positive. And if the slope of f prime of x is decreasing, then f double prime is negative. Okay, here the slope of f double prime of x is equal to f triple prime of x, which we don't bother with. That doesn't tell us really any information about the original. Okay. So the y value in f of x is the position at x. Right? So the y value of a function is the position at the value x. The y value in the derivative tells you if you're increasing or decreasing, right? So it tells you if your original graph is increasing or decreasing. So if f prime of x is greater than 0, then f of x is increasing. If f prime of x is less than 0, then f of x is decreasing. Right? So it tells you the slope of f of x. Now if f double prime of x is increasing, then that tells you if f of x is concave up, And if f double prime of x is decreasing, or is less than 0, then that means that f of x is concave down. Okay. So using that information, we are going to do 2 example problems on the next 2 pages. So the first example problem says f prime of x is equal to 4x cubed minus 12x squared. We want the critical values. So critical values means that we're looking for when f prime of x is equal to 0. So we're given f prime of x up here. So we just want when 4x cubed minus 12x squared is equal to 0. So when we factor, we get 4x squared times x minus 3 equals 0. So x is either 0 or x is 3. So those are our critical points. So now we want to figure out when f of x is increasing and decreasing. So we're going to create our number line. We know we want 0 and 3 because those are our critical points, and our domain isn't given, so we're going negative infinity to positive infinity. So if we choose some test numbers, so if I chose negative 1, 1, and 4, and plug it into our derivative, and we'll find that we get a negative number, and then a positive number. So we know that there's no switch happening at x equals 0. So no change at x equals 0. But at x equals 3, we go from being negative to positive. So at x equals 3, we have a local minimum. Okay. So now for part C, we want to find inflection points. So inflection points means we're looking for when f double prime of x is equal to 0. So we need to find f double prime of x, which we know is going to be 12x squared minus 24x. So we want that to equal 0. So when we factor out a 12x, get 12x times x minus 2. So x is equal to 0 or x is equal to 2. So we're going to make another number line from negative infinity to positive infinity. And on that number line, we'll have 0 and 2 for our inflection points. And if we pick some test values, we have negative 1, 1, and 3. And if we plug those into our second derivative, we'll have a positive number, a negative number, and then a positive number. Which means that from negative infinity to 0 in this whole space, we're going to be concave up. From 0 to 2, we'll be concave down. And from 2 to infinity, we'll be concave up. So if we put these two number lines together, that'll give us all the information that we need to know to help us graph or sketch a graph of f of x. So I'm going to make one big number line, and I'm going to put both my inflection points and my critical points on this number line. So I know my critical points were 0 and 3. So we have 0 and we have 3. My inflection points were 0 and 2. So I'll just need to add a 2. Okay, so here's negative infinity, here's infinity. So up top, I'm going to put what my derivative was doing for my first derivative test, and on the bottom, I'll put what my second derivative test told me was happening. So my first derivative test says that from negative infinity to 0, we have a negative f prime. Okay, so from negative infinity to 0, we have a negative f prime, which means that we're decreasing. Okay, from 0 to 3, we had a negative f prime, which means that we're still decreasing. So from 0 to 3, we had negative, so we were still decreasing. And then from 3 to infinity, we had a positive, so then we started increasing. Okay. Now, my second derivative test told me that from negative infinity to 0, we had a positive second derivative, which means we were concave up. From 0 to 2, we were negative, so we were concave down. And then from 2 to positive infinity, we were positive, so we were concave up. So what I'm going to do is now my number line is split into 4 different intervals. And each interval tells me 2 pieces of information: increasing, decreasing, and concavity. And looking at our table from the first page, we can draw or sketch what that part of the graph should look like. So if we're decreasing and concave up, we know that our graph should look like so. Now if we're decreasing and concave down, then our graph will look like this. Now if we're decreasing and concave up, our graph will look like this. Oops, sorry. Decreasing, concave up, graph looks like that. And then if we're increasing and concave up, then our graph will look like that. So we're going to put all 4 of these pieces together on this graph at the different points. So we have 0, we have 2, 3, and then this goes on for infinity. So from infinity to 0, our graph wants to look like that. So let's make that happen. From 0 to 2, our graph wants to look like that. So let's make that happen. From 2 to 3, our graph wants to look like that. So let's make that happen. And then from 3 to infinity, our graph wants to look like that. So let's make that happen. And there's a sketch of what f of x could possibly look like. Granted, if you started at a different point, or if you lengthened your lines, your graph might look a little bit different, but that's a general sketch of what the graph should look like for f of x. Okay. For our second and last example of this packet, we have the graph of the derivative. So this is f prime. And we want to find the critical numbers. So again, critical numbers means when f prime of x is equal to 0. That happens here, here, and here. So our critical numbers are when x equals -4, x equals 1, and when x equals 3. The next piece says find intervals when f of x is increasing and intervals when f of x is decreasing. So if we draw our number line, we're going from -4 to 4. We know our critical points are -4, 1, and 3. And if we're looking for when it's increasing and decreasing, increasing is when f prime of x is greater than 0. Decreasing is when f prime of x is less than 0. So on this graph, we're increasing when our line is above the x-axis, because this is f prime, and we're decreasing when our line is below the x-axis. So from -4 to 1, we're increasing. From 1 to 3, we're decreasing, and from 3 to 4, we're increasing. So now we want to know, where does f of x have a local max or a local min? So again, we have critical numbers, -4, 1, 3, and 4. So let's start with our interior critical points. So when x is 1, we're going from positive to negative. So therefore we have a local max. When x is 3, we're going from negative to positive, so we have a local min. At the endpoints, x is -4, so x has to start somewhere and then start increasing. So if we're starting somewhere and then going up, then we have to have a local minimum to start at. And then at the very end, when x is 4, from x is 3, we started going up and we never stopped, so this must be a local max. Okay, so for part D, we want to find the inflection points. So inflection means that we're looking for f double prime of x equaling 0. So just a reminder, f double prime of x is the slope of f prime of x. So we want to know when the slope of f prime of x is equal to 0. So if we go back to our graph, we're looking for when we have a horizontal line for a slope. That happens here, here, and here. So that's x equals -3, x equals -1.5, and x equals 2. And we want to know if it's concave up or concave down. So concave up means that f double prime of x is greater than 0. Concave down means f double prime of x is less than 0. So I'm going to make my number line from -4 to 4 and add my inflection points. And looking at the graph, right, f double prime is the slope of this graph. So from 0 to -3, my slope is increasing. So my slope is positive. From -3 to -1.5, slope is still increasing, so positive. From 1.5 to 2, we're decreasing, so negative. And from 2 to 4, we're increasing, so positive. So from -4 to -3, we're concave up. From -3 to -1.5, we're still concave up. From -1.5 to 2, we're concave down. And from 2 to 4, we're concave up. So now we want to sketch a possible graph for f of x. So here, again, if we're going to sketch the graph, we need all our inflection and critical points on one number line. So we know we're going from -4 to 4. Our critical points are 3 and 1, and our inflection points are -3, negative 1.5, and 2. Okay, so on the top, I'm going to put my first derivative test. On the bottom, I'll put my second derivative test, and I'm going to use both of those pieces of information to help me sketch this graph. So on the top, we know that from negative 4 to 1, we had a positive first derivative test. So all the way across until I get to 1, we're all positives. We know that from 1 to 3, we had a negative first derivative test. So until I get to 3, we're negative. And then from 3 to 4, we're positive again. And then for our second derivative test, from negative 4 to negative 3, we were positive. From negative 3 to negative 1.5, we were still positive. From negative 1.5 to 2, we were negative. From 2 to 4, we're positive. Alright, so I'm going to sketch what each section of this graph should look like. So positive, positive means that our graph should look like that. Positive, positive, our graph should look like that. Positive, negative, graph should look like that. Negative, negative, our graph should look like that. Negative, positive, graph should look like this. And positive, positive should have an end of our graph that looks like that. Okay, so this wants us to start at 0, 0. So at 0, 0, between negative 1.5 and 1, our graph looks like this. So if I start numbering graph, so from negative 1.5 to 1, our graph should look like this. I'm just going to make sure that that passes through 0, 0. Okay, so from there, so from 1 to 2, we know our graph should look like that. From 2 to 3, we want to kind of curve it. From 3 to 4, we're going up. Okay, and then working backwards, from negative 3 to negative 1.5, we want our graph to look like this. And then from negative 4 to negative 3, we're still looking the same way. So this is what a sketch of f of x would look like.